I recently acquired a 300-pound high-voltage pulse discharge capacitor, which can store up to 50 kilojoules of electrical energy. It's rated at 200 microfarads and 22 kilovolts. For context, defibrillator capacitors can store a few hundred joules, and while they can revive you in the right circumstances, they can also be lethal in the wrong circumstances. This capacitor, on the other hand, will only kill you. I have some exciting projects planned for this capacitor, but before I so much as remove the shorting strap, I need a safety discharge stick that's capable of discharging its full rated energy. These discharge or grounding sticks can be purchased from a variety of vendors, but are most often used for grounding high voltage systems and do not always have a resistor rated to discharge tens of kilojoules in a few seconds. The ones that do typically cost a few $1,000s. We can learn a few things from the design of the off-the-shelf options. The generic format that they all have in common is a long fiberglass handle with a ground cable connected to a hook or a straight metallic end fitting. In our case, we want a high voltage, high energy resistor between the ground cable and the end fitting. In this video, I'll show you how to build a DIY high energy discharge stick with mostly hardware store parts. My design follows the same basic layout as the commercial options with a few cost-saving tricks. For the handle, we want a stiff, non-conducting rod or tube. While wood might seem like it meets this criteria, it is not a reliable insulator at high voltages. Fiberglass is the ideal option as it's a good insulator and it's quite stiff. Unfortunately, fiberglass tubes and rods of suitable diameter are not readily available or cheap. When DIYing cheap versions of expensive things, I always brainstorm what other product already is the thing that I'm looking for. In this case, rather than trying to find fiberglass tube stock, I went to Lowe's and bought a fiberglass tool handle for 17 bucks. The heart of the safety discharge stick is the high energy resistor. If you selected a wooden handle in step 1, you can skip this step, as you will be the high energy resistor. While almost all commercial options will use a bulk ceramic resistor, like those manufactured by HVR, these are not easily acquired by the hobbyist and are not cheap either. The core principle of this resistor is that the resistive element has a very large thermal mass, which allows it to absorb tens or even hundreds of kilojoules in a matter of seconds without overheating. The best DIY candidate I found is a copper sulfate water resistor. PulsedPower.net has a handy online calculator that will help you determine the parameters of your water resistor. For my requirements, I started with a ballpark resistance value that would allow me to discharge my capacitor in a matter of seconds rather than minutes. In my case, I shot for around 10 kiloohms, which gives me an RC time constant of 2 seconds, meaning my capacitor will discharge over 99% in 5 time constants, or 10 seconds. Next, I decided on a target water volume of about 500 milliliters, which would allow me to dissipate the full 50 kilojoules with only a 24°C temperature rise. I was able to meet both of these requirements with a 5-foot length of 3/4-inch ID tubing filled with a 17 grams per liter solution of water and copper sulfate. Constructing this resistor was fairly straightforward, again with hardware store parts, but I learned a few tips along the way that you might find useful. I used 3/4-inch ID, 1-inch OD vinyl tubing, brass barbed hose fittings, and brass NPT end caps. The brass fittings act both as a seal and an electrical terminal, as they will be in contact with the copper sulfate solution. In order to be able to use the brass end caps as electrical terminals, I wanted a tapped 1/4-20 hole in the end. I was able to drill and tap the thin cap top, install a screw, and fill the void with solder. This provides a watertight seal as well as some extra support for the threaded connection. Next, I created my copper sulfate resistive solution by dissolving 18 grams of copper sulfate in 1 liter of water. I installed the barbed fittings on each end of the tube and used hose clamps to prevent leaks. I installed one end cap and poured my copper sulfate solution in from the other end, making sure to fill it all the way to the top before screwing on the second end cap. It's important to have as little air as possible to ensure constant electrical contact with both brass end fittings, no matter the resistor's orientation. In order to mount the resistor to the fiberglass handle, I modeled a 3D printable part that would fit snugly on the end of the handle with a helical groove around the outside to guide the resistor tubing. I included 2 holes to allow the part to be bolted to the handle and pathways to allow the resistor to be secured with zip ties. If I could do it again, I might have gone with a longer section of smaller diameter tubing, The reason being, this 1-inch OD tubing was very hard to bend around this 4-inch diameter mandrel without kinking it. A trick I learned is to fill and cap the tubing first so that its interior volume cannot change, which will prevent kinking. Then, put the whole thing in a pot of boiling water for several minutes to soften the vinyl tubing. Once al dente, remove the tubing and begin wrapping it around the mandrel, securing it with zip ties as you go. The hot, softened tube will stretch as needed in order to create the bend radius while maintaining constant volume. With the resistor completed and mounted, it's a good time to check its resistance. I had read online that it could take more voltage than a multimeter can apply to get an accurate resistance measurement, so I hooked it up to one of my high voltage supplies set to 150 volts and read 28 milliamps of current for a resistance of about 5300 ohms. This was quite a bit lower than I expected, so I hooked it up to my bench multimeter to take a closer look. It agreed with the previous measurement, but also revealed that the resistance was steadily climbing. That's when I realized that it must be fairly temperature dependent and is reading low fresh out of the pot. Sure enough, its resistance slowly climbed as it came down to room temperature, settling around 8 kiloohms, which isn't too far off my target. Since the preliminary checkout looked good, I put the final touches on. In order to mount a metal end fitting, I used a heat set 1/4-20 insert. Then I created a jumper from the top of the resistor to a length of brass all thread screwed into the insert. I cut 15 feet of 10 gauge high voltage cable with a large clamp on one end for the ground lead, and 3D printed some clip-on mounts to keep it tidy. For its first discharge test, I used a 4 microfarad capacitor charged to 20 kV. This should result in a peak current of only a couple of amps and a discharge time on the order of 100 milliseconds. Despite the low current, the arc still makes a pretty crisp snap when it strikes. You can see the charge and discharge voltage waveforms confirming operation as expected. I have not tested this with my big capacitor yet, as I want to complete construction of a more controlled test setup first. Be sure to stay tuned for a series of videos where I use this capacitor to build a microcosm of a professional pulsed power system, hopefully culminating in a coin shrinker.